Mostly we do it for non-profit. So you know, and from 2019 onwards, we are partners of the Italian Association for Machine Learning. So and also we do collaborate with other people as well. So we have like a couple of events coming. October 27 to 29 we have this one, and 24th to 26th November we have these code motion events. So feel free to grab the tickets, and if you want to attend these. So anyway, so I'm going to talk about this one after this talk. Let's get jump through it. So today we talk about reinforcement learning, and I'm pretty sure that you heard reinforcement learning, like if you're into AI. So today we talk about reinforcement learning. What is reinforcement learning? How? Why? So I just want to give you the high level idea of what reinforcement learning is for beginners as well as deep. We're gonna go deep. If you are comfortable with that, even I can talk about a little math under the hood. What's gonna happen? So so just want to check like if you have any questions, how we can hear you, how we can hear you. It's nothing much. So all right. So yeah, so second we talk about MDP, Markov decision process. MDP is kind of like a framework to do reinforcement learning. So it's kind of like a philosophical thought and approach to solve problems with reinforcement learning. So it is a must. It's a must for everyone who's into reinforcement learning. So we're going to talk about that, and then I'll talk about a little bit of terminologies, like what reinforcement learning, like what kind of things we do in reinforcement learning, how that's related to the deep learning and machine learning. So I'll introduce some of the terminologies like policy and value functions and etc. 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 So, and fourth one, we talk about the kind of task, like what kind of task we do with machine learning. In deep learning, we do, in machine learning in general, we have like two different kind of tasks. One is in supervised learning, one is regression, another is classification. Similarly, in reinforcement learning also we have different tasks. We'll talk about those tasks. So, and finally I talk about QLearning algorithm. Reinforcement learning is pretty big, so unfortunately I can't cover everything in 1 hour in one particular session. So, but I'm going to talk about important algorithm, which is QLearning. So that's what we're going to do today. And I talk about deep QLearning. So QLearning is a basic algorithm, but deep QLearning uses deep neural networks. So fundamentally they are same, but the way we approach, the way we solve problem are different. So yeah, that's pretty much it for this session. Like for in 1 hour I'll try to explain all of these concepts. So before I do that, I just want to give you kind of like a warning or alert or something like that. So reinforcement learning is pretty big. Obviously I can't cover everything in one go, so I'll try to approach this problem in a way. First I'm going to talk, I'm going to give you like overall idea of what reinforcement learning is. Then I'll go into little details, like little bit of math if you're familiar, and then we're going to go deep dive in even deeper. Then we can proceed the code also. So I'm going to skip talking about myself. I'll talk about myself after the talk. So but anyway, slides are that you can pretty much see later. So the first thing is, before I expect that you all are aware of what machine learning, what supervised learning and supervised learning do. So in supervised learning, if I have to summarize it, so in supervised learning we'll basically learn the mapping between futures and targets. Like you have X, you have Y, all you have to know is the mapping function between X and Y. Futures, targets or labels different. So that's what we see pretty much every day. Supervised learning is pretty accurate, pretty fast, so we use a lot of time. So unsupervised learning is a little bit difficult. So here we don't have the targets, we don't have the labels, we just have the raw data, and we're going to try to figure out the patterns in that raw data. Unsupervised learning is not much used, but from the goals perspective, from a goals perspective, it's a long road for us to be able to solve problems using unsupervised methods. So reinforcement learning is kind of like a completely different, at the same time kind of related to machine learning. So reinforcement learning is a process of accomplishing a task by trying and failing at the task, like trial and error. So just like human beings, so if you want to learn something, if you don't get it in the beginning, you try one more time, so you understand a little bit, so you try next time, so at the, like, let's say after trying a couple of times, then you understand what's going on. The similar reinforcement learning also mimics, but for humans we take very less time, but computers take a lot of time. So they have to trial and error like thousands, even millions of times in order to do a simple task. But again, it depends on the task. So this is the high level idea of what reinforcement learning is. For example, we learn video games. The way we learn video games, we interact with the game environments, right? The same way also reinforcement learning algorithms interact with the game environments. So just the way we do it, our machine also could do the same, but machine takes a lot of trial and errors. We only do a few. So, and also it says that kind of like a AI, it's like AGI basically. So it's not based on particular data. It's like reinforcement learning algorithms are not based on specific data. It's based on experiences. So like learning from data is pretty much what we do in like in machine learning, in deep learning in general. But here not only we learn from the data, you learn from the experiences. So those experiences may or may like sometimes they may correlate, sometimes they may not. So it's kind of really hard to tell where the reinforcement learning is exactly used in AI. But in the long term, it goes into the path of AGI, like we try to understand the general intelligence of it. So AGI is kind of, if you think AGI is a goal, reinforcement learning is definitely one of the parts to take us to these AGI. So so this is how the reinforcement learning algorithm works. I'm just going to talk a little bit about the terminologies here, because in machine learning, in deep learning, you don't really use these words at all, but in deep learning they are really extremely they're used all the time. So here we call agent. Agent means one particular system or program, you can call. An environment is basically the kind of domain that we are focused on. For example, if you're focused on a video game, if you're trying to create a video game, so the video game is the environment, basically what kind of controls they are. But if you're trying to apply reinforcement learning to a particular domain, let's say finance domain or healthcare domain or any other domain, the environment must be the for example, finance domain, the finance domain's data, finance domain stuff like that. So environment is fully based on the domain, like where you want to apply our reinforcement learning. An agent is something that we like is a system or a process, or like just like an input. So what agent does, agent actually observes the environment and takes some actions, and based on the actions, environment gives some rewards to agent, and this loop goes. That's it. So if you're an agent, for example, if you're trying to accomplish a simple task, for example, let's say walking, just think about like you want to walk, okay, let's think about like a kid wants to walk. The environment is just a normal floor, or maybe slippery environment, maybe different kind of environment you think. So every time the baby takes a step, let's say you give a chocolate, you give a candy, you give something as a reward. So what the baby does is, the baby first takes, let's say, left leg or right leg. Baby does some actions, either put forward left leg or right leg. So on the environment, then it observes it. Then based on the feeling, the baby tries to make another move. So every move we give, we reward. So the baby is incentivized to keep walking, keep steadily, and So the same example here also here works. So a computer program is going to try to interact with an environment that we provide. In the environment, the program takes some actions, and based on the environment, we give some rewards, and the loop goes on and on. So the goal, for example, we define a goal for any agent. For example, if you have one agent, we define a goal. What's the goal of that agent is? For example, here I say playing chess game and understanding how it works. So the environment is the, let's say, chessboard, and we just the goal is to beat the opponent, or play the chess game. The environment, of course, the chessboard pieces and other stuff, and actions, like what are the possible moves for every piece, like you have pawn, you have for all chess pieces we give moves. And of course we can set up reward system. For example, you can either say you get positive reward, let's say 10 points if it wins, or minus 10 if it lost, or you can give an immediate reward, like for example when you make a move, when you kill the opponent, maybe you can give 10. So these rewards and these actions, these environment, these goals, all are custom based, which means you can apply these to any other domain. Just like I said, finance domain, if you take finance domain as environment, you can give the goal for finance domain. Let's say I want, for example, you're predicting a stock market price. Let's say that you're predicting stock market. So you can tell that is a goal for an agent. The environment is you give enough data to be able to predict, or to be able to accomplish the goal, and you can define some actions based on it, and you give rewards. Let's say 10 points, 20 points. So it's fully custom. You can customize however way you want, wherever you want. So reinforcement learning, you can apply any domain. If you have some domain expertise, some domain knowledge, you can apply anywhere. So it's obvious. The agent wants to learn. The agent's goal is to get the bigger reward as possible, right? So the agent tries like a couple of times, tens, hundreds of times, basically to improve the performance, to get the bigger rewards in the possible. So that's the high level idea of what reinforcement learning is. Before I move there, I just want to check if I have any questions, then I'll okay, if you have any questions, let me know so far about reinforcement learning. So I'll take. So I just want to summarize it. In supervised, we give the features and we give the targets. We try to learn the mapping between those two. That's it. If we give, for example, in computer vision, if you give input images, let's say cat, and you want to predict by cats, then you give the targets as cats labels. In unsupervised learning, we don't really have labels. We just give raw data. For example, you give speech data or text data or even any other data that you don't have any labels. It tries to find the patterns in the data and gives some conclusions based on the patterns. So reinforcement learning, the other hand, it doesn't work that way. Any task you define, the goal of RL algorithm is to try to accomplish the task by performing some actions, and of course based on the environment we need to design in a way that you need to have the reward system, you need to have environment setup, you need to have actions. So if you set up that process, the RL algorithms are going to try to kind of mimic the human process and learn over time. So that's the high level idea, and this is just like it's very popular, I think, picture what reinforcement learning is all about on internet. So I just want to share the same thing only. So yes, so now I want to talk about MDP, because this is really important, because you can understand reinforcement learning anywhere because it's popular. MDP is something that you need to pay a close attention. So as I said in the beginning, MDP is just like a framework to solve RL problems. So if you wanna solve any particular problem that which is required reinforcement learning, you got to crack the MDP version of it right before. So MDP is also pretty big. I'm not going to talk about all the math behind it, but I'll talk the math that is necessary for the algorithm that we're going to build. So, and that's all. So but if you want to know more about MDP, just make sure to check it out on the internet. There's a tons of math in there, but I'll try to simplify it a bit. So one of the important things of MDP is like the property called Markov property. Basically it says that okay, this, I'm just going to read it out. The future is independent of the past given present. So it means knowing what happens in the past does not necessarily change the way the future is going to be given the present. So which means the present state of the algorithm or present state of the system is more important than what happens in the past. So what happens in the past, you can literally throw the past. All you have to focus in, where are you, what's the present state or present situation. It's kind of like a philosophical thought as well. So which means knowing the current state of the agent can help the agent make a move, like what action to take next. And the entire past history, you can ignore the entire past. So it has like five major components. Like here I define it. One is a set of states in the environment. For example, if you think the chessboard example, the environment is what are the states for every piece. A pawn can move forward one step or two step, depends where it is. So you define all set of states in the environment in a set we call S here, and A is like a set of actions an agent can take in the environment. Again, the same example, pawn can take certain actions in the chessboard. Maybe the other piece of the chess cannot take. So again, we collect all the set of actions, we put it in one function, one bigger set, let's say A. And P, you don't really need to know what transition probability matrix at this time, because it's basically a matrix for states and actions. At this time we can probably ignore transition probability matrix. If interested, probably I'll touch later. And the next one is reward component, of course. So basically the way you however you want to set the reward, you just give that to this function or to this component. And the last but not least is discount factor with gamma, and this is something I'll talk a little later because this seems a little confusing in the beginning. So I'll talk about discount factor a little later, but basically you need to understand S, A, R, set of states, set of actions, and the reward component or reward function R. So so we are aware of the MDP has 5 components. If you have these 5 components basically, or let's say you can ignore P, if you have these 4 components, you can solve RL problem. For example, if you think of any problem, like just like I said, domain, fintech domain, or any other domain, if you think some problem is there, if you can figure out the set of states for that problem, set of actions for that problem, set of rewards for that problem, and that's it, you can pretty much apply reinforcement learning to that particular domain or that particular task. So mostly RL is used for kind of simulating the like game environments, which is what we usually see on internet and everywhere, because it's very visually it's appealing. But if you work in a domain, any domain, if you see any problem has set of states or set of actions, rewards, you can somehow apply RL over there. So just want to tell you. So this is not for only for video games. This is for even real-time data. So any domain you work on, you can pretty much apply that. I cannot stress this enough, but it's really powerful, I think. All right, I'm just gonna move of course the reinforcement learning goal is to get the maximum reward in the future. So that means if the main goal is to get the maximum reward in the future or in the environment. So that's the goal of any reinforcement learning problem. So here a little bit math. If you are not familiar, then it's very easy. Given a state, you just expect what's the reward going to be. That's it. For example, if in the state of chess, let's say you see a chessboard with kind of like different states, and given a particular state, you try to expect the reward. What reward I get from this state onwards? You basically expect it. So of course you take more actions, more states, and again, so then that's going to be like this: reward at the time step 1, plus reward at time step 2 and all the way, and you predict this one. Basically you expect it. I mean, it's not the it's not how how exactly the game is going to work, but it's just the way you think it's going to work. The reward function is basically it's going to like for okay, for I think I might miss what yeah, all right, here. So the maximum expected cumulative reward we denoted with the G at time step t would be for all future time steps. At this time step, it would expect basically what's going to happen in the future for all time steps in the future. So for example, if you had at step t, the reward would be next step, and so on. So the same thing is like it's written right here. M is like a state, let's say state 0, like at the beginning you are, and of course you can have as many states. If it's a game, of course you have very limited states, maybe 10, 20, 30, 40, maybe 100. A game eventually ends. If it's not a game, for example stock market, then and it's going to be continuous, so it's not going to end anywhere, so that's why infinite is there. And if you combine all of them, you expect this is the total. And just like I said last, here I talk about the gamma. So gamma is a discount factor. Typically is between 0 and 1. Basically what they do, why gamma is introduced is we want to give some discounts in the futures basically. So if the gamma is pretty much 0, that means the agent is trained to lend the short-term reward. If the gamma is set as 1, then the agent is trained to get the long-term reward. That means the agent is going to explore a lot in the environment to maximize the reward as much as possible. So we need to adjust this gamma in a way that how the future events are going to be placed. So I think gamma is theoretically it's kind of doesn't make sense to understand, but practically gamma is pretty much important to apply in RL problem. I think I'll talk about I think gamma when I show you some code, because theoretically it makes sense, but still you don't get the intuition like why gamma is used. So just want to summarize MDP. If you have any questions, I'll probably take. Okay, I'll take some questions. What commercial application do you think are good fit for RL, useful normal companies, mean outside the Boston Dynamics types and self-driving cars? All right. So the question here says that what kind of commercial applications do you think are good fit for RL today, other than the Boston Dynamics types and self-driving cars? So so majority of the RL algorithms, as I said in the beginning, we use for simulate the game environments, because for example even self-driving car or even Boston Dynamics, we have a robot or like hands or stuff. We try to kind of like a create robot to try to walk or try to do certain action or try to do something. So that's what we do, and we've been really going well. But as I said, RL can also be, so I'll talk about the commercial application here in this point. RL, as I said, RL can also be applied to any particular problem where you can set up the environment, set of actions and set of states, and if you somehow figure out what's the variable, or like what's the reward function, if you can set a reward function for this, and there you can apply. So I'll try to the most common example that I see, the common problems I see when I discover RL is basically a stock market data or any other finance data. So for example, if you want to predict something, let's think about the machine learning approach in supervised way. If you want to predict a particular value, let's say you give x, I want to predict a number y. So of course in supervised learning what we do, we take the all past x, we give to y. The same problem here what we do is, when we want to predict y, we don't really care about the data now, like what is x. We care about like how to approach how to solve this y. So what is the environment, how to create environment that can solve where you can actually place y in center and create some reward system, create some state system, create some action system, kind of make it like a environment to solve that y. So same prediction problem. For example, if you want to predict from x to y, just like supervised learning, you can pretty much do that taking x values. But if you want to predict y, you ignore x, you create an environment around it. So if it is a stock data, you create environment in a way that, for example, if it's predict stock well, then I'm going to give you a point of a plus 1. So that it's like I write a function in a way that if it predicts correctly or anywhere correctly, then I'll give you plus 1 reward. Kind of like you try to codify, try to create a game out of it. So stock market data or even health. So in order to create AI applications that can actually improve the like kind of couple of existing models you can create. Basically, ultimately, I would summarize this: for any particular problem, you can apply RL to any particular problem. Any problem, if you can figure out states, actions, reward system. So it's like this. I'll try to give you a real-time example. Let's think about if you have a kid, and the kid, let's say 10-year-old kid or something like that. So the kid wants something, like kid wants a candy or kid wants money or whatever. I'm just making this example right now. So you don't give directly whatever thing the kid is asking you. You try to create a game out of it. For example, let's say a kid wants to have some money. You say to the kid, hey, if you behave good, if you're doing good, if you're doing your homework, if you're doing that, this and that, I'll give you whatever you ask. So that's how this thing works. If any problem, if you have, what you have to do, you don't really directly jump into solving that problem. Just like supervised learning, you try to create an environment for that particular problem, and you try to code it in a way that the problem has to solve itself, basically, by just following the rules you set. By following the rules means like following the rewards, following the actions, following the states. So the applications, I would say, basically endless. You can pretty much apply RL to anything you can visualize. So I don't have any particular example other than the markets and other than the finance data, but I'm pretty sure that I can give like a little later. So how do you benchmark performance of RL agent to say deployment in prod, and how different it is used versus super learning algorithms? For example, a supply chain agent with policy learn. All right, I think that's really a broad question. Like, how do you benchmark performance of RL agent? So unfortunately, we don't have any kind of like metrics to check the performance of reinforcement learning algorithms. For example, in machine learning, we have at least you have accuracy, you have scores. You can have people come up with different kind of metric techniques to improve the performance of the models, performance of the environment. But since RL is fully customized solutions, there are like very few. I don't think there is any particular metric to measure, but you can measure the performance for your particular problem that may not be applicable for other problem as well. So it's kind of really hard to measure the performance, but if you want to apply this on production level, what you have to do is, I think this is going to take a little bit more time, so I'll try to summarize it. So in order to set the performance, you will have to create two different like agents, basically, or multiple agents. So every agent is going to learn individually, basically, with the same data, with the same approach, but they are completely independent. Basically, let's say you try to solve a task, but instead of doing one agent, you try to create multiple agents. Basically, you don't with the same data, with the same environment, no change at all, but these changes don't interact with each other. They are completely independent. So now you try to evaluate the performance of every agent right now. Let's say agent 1 gives kind of really good, agent 2 might do even better, or agent 3 may be bad. So you try to code all of these individual pieces, and you try to see which one works really well, basically. So basically you're trying to create a multi-agent system. Basically you try to create a lot of agents, and you take the one that you think is fit, or you can even merge two of them basically, or you can even merge even more. It actually depends on the problem, but I would say that the performance can be measured based on how the agents performing compared to other agents. Basically this is the approach probably I've seen, I've used, but other than that I don't think, to my knowledge, in general I don't think there is any way to improve the performance other than manually checking with multiple agents. All right, so yeah, so then I'm gonna so the concepts, I'm going to talk about the reinforcement learning concept because these are pretty much important. These only you use a lot of times. So again, these terminologies you may have heard before or you may not, but I'll try to simplify it. So one is policy. They call policy pi, or policy function, or policy generator, policy algorithm. Policy means kind of like a strategy, so that maps from state to action. For example, if just think like a policy is a black box, or a function. You give an input, you get an output. So the input is state, you give the state, what state you are in, and the policy is going to determine the action, what action to take. If of course if the policy function is good, then obviously it gives the good action. If the policy is bad, basically it gives the bad action. Basically you can think that policy function or policy is like a kind of either network or a function, simple function. It tries to figure out which state from which state to map which action. That's it. So there are like two types. One is like deterministic policy and stochastic policy. Mostly we used stochastic policies. So deterministic policy is like it gives a particular action complete 100%. For example, if you give a particular state, it can tell you what action to take 100%. So for example, if you want to move right or left, let's say imagine a game where you have to move right or left. So it gives an action like either you have to move right, you have to move left. Basically it doesn't say that you have to move like 40% right, 30% left. It doesn't say it. It says that either you go left or right. So stochastic policy, just like I said, it gives the policy based on the probabilities. So it can say either somewhere, you have to go 60% right, 40% left. So you choose whether you should go for 60% or 40% based on the way you write the code. But it gives some probabilities for every action. So again, one more time, I just want to summarize it. Policy is a function or a network. You can call it deep network, or you can call it a function. It doesn't matter this time. Where it takes the state and gives the action. Of course, for any RL algorithm to work well, you need to have great policy. That means great strategy you can have. So the other one is a value function. So value function is basically, it's similar to a reward function we have seen before. It's like it's going to expect the future reward by following some policy file. So by following some strategy, whatever strategy that works, it tries to estimate the future reward, expected future reward basically. This is what we have already seen. So g of t can be calculated by taking the immediate rewards, like for the next step, t plus 1, t plus 2, and so on. Again, for this also it requires only the state. You input is state, you give the input, and it gives some estimation score. Let's say you give a state, it gives some value. Example. Again, here there are two types. One is like state value function, and second one action value function. You can see in the next slide how this works, but I'll try to give you. So state value function determines that how good it is for the agent to be in a given state. For example, you are at one state and you want to verify, okay, which state is good basically. For example, let me give you an example. Let's say you are I'm sorry. I think if okay, let's say you are at this point state, so you want to go down, so you are either you can take this, you can go this way or you can go this way. Let's say this is a state, there are 4 states, so you are at this state. So what state value function does, it tries to it actually tells that which state is good to be, either this state or this state or this state. That's what basically state value function does. While action value says that it determines that how good it is to perform a given action basically in a given state. So if we go back here, action value says that you have 3 actions. For example, if you take action 1, action 2, let's say action 3, so if you take action 1, that means it goes this state. If you take action 2, you go to this state. If you take action 3, it goes to this state. So action value function tells that which action to take basically, instead of focusing on which state to be, it focuses on which action to take. That's it. For this, input is what state you are in and what action to take. So if it's confusing, you will see in a bit, like how those work. Basically both of them tell the same thing. Only thing difference is like input. So these slides I took it from David Silver. If you guys don't know who David Silver is, he's one of the best RL probably at DeepMind. Actually he taught like many kind of courses in reinforcement learning, so I took this slide from him. So again, it same thing, state value function and action value function. So if this is confusing, just imagine that you, for any input for any particular program, you give a state, it can give you estimation reward function or reward value basically. If you give state as, it gives you some score. That's by following some particular strategy, which is we call pi. While action value, it takes 2 parameters, gives the same score. So ultimately both are same in terms of doing in terms of expecting the future reward, but the only thing is the extra parameter is added. Based on the extra parameter, it makes some decisions. So mostly we use like action value function a lot, because because most of the time when we have states, we also have actions, so it's better to use 2 input parameters and make some decision than 1 input parameter. So of course these things may be kind of complicated if you're a beginner, but I'll try to simplify it. So basically for state value function, these okay, I think it's better if I show. So let's say state value function V, let's say you have like 3 states or 4 states. So V calculates the score for every state. Let's say this score is 20. Example, I'm making these numbers up, I'm sorry. 10, maybe 3, or maybe 4. So state 1, state 2, state 3, state 4. So this is what V predicts it, V expects it. For example, for every state, it kind of predicts a future reward. Maybe for if it 1 state, you get the future reward 20, 2 state we get 10, 3 is 3, 4 is 4 basically. Same thing for action also. Action also does the same thing. You have 4, again let's say 4, but it takes the extra input is action, that's it. So that's the only difference. And the star is for the optimal, which means the best policy. That means this is what we want to know. So of course we iterate the algorithm many times to improve the performance, and at the end we want to have the optimal policy, optimal behavior, optimal value function that can that can do really well. So I'll talk about these things later. I think you can understand these things by just looking at the code than just seeing it here. So again, some other concepts in reinforcement learning. So just like in supervised learning, we have like two tasks basically in supervised learning, right? One is like you can either classify or you can predict. You can do like regression and classification. Here in RL we have two tasks. One is prediction and control. Prediction is it predicts the kind of a number, a numeric value basically. Here we call like total reward basically. So the prediction task is like if you want to predict some some number, some total reward for any state, and that task is called like prediction task. For example, here the strategy is given, that means the policy is given. You can think policy as a function. All you have to give is state, it gives you an action, best action basically. So based on some policy is given, some policy you follow here, it tries to calculate the value function vpi. Without, okay, you can ignore with or without model. That's a little complicated to explain at this time since we skipped the without model. So I'll try to simplify it. The policy is given, like means a policy function you can think as input. You give state, it gives you best action, and the prediction task is the task that where you can predict a total reward, basically expected reward. While the control task is like it's going to find the optimal policy that maximizes the expected reward basically. So here you give some policy that's not a best policy, that's just like a random policy in the beginning, and it tries to optimize that policy to discover the maximum to get the maximum total expected reward. So in a way that some policy is given, it tries to optimize the policy to get the best score. Here it just policy is given, all you have to do is get the total expected reward. So I'll show you later like in what prediction and control. I think we understand when I go through the code. So again, one more task, one more like a concept in reinforcement learning, on policy learning and off policy learning. The name itself, it says that on policy learning is like it learns on the job, which means you can take a policy, let's say random policy or random function, it tries to optimize that policy, tries to improve itself on the job. So off policies is different. It has like we can have two policies, target policy and behavior policy. It uses one policy to improve the other policy basically. So here I defined the target policies and behavior policies. So behavior policies is what we it basically tries to learn the environment, while target policy is to improve that improve this behavior policy basically. So you can think like two policies, two different functions are using. One function job is to improve the other function, and the other function job is to interact with the environment basically. And one more concept here, which is exploration and exploitation trade-off. This is probably one of the big concepts in reinforcement learning because one of the main thing of I think in real time when we solve problems, the states and actions are most like probably infinite states you can have for any particular task, or maybe infinite actions you can take. For example, just imagine playing a simple video game. Either you can go right, you can go left, or you can shoot. Here the states are pretty much like you can control the states. You can have like a limited states like 5, 10, 20, but if you have a bigger space, like let's think of real 3D world, 3D game. Here kind of like states, we can't really limit the states, we can't really limit the actions. The state space and action space is pretty big. So here we need to do a lot of exploration while we are playing really good in the game. So this is where the exploration trade-off comes. So in reinforcement learning we have to balance these two, because if you don't explore much, that means you don't really discover bigger rewards. if you don't explore, that's the problem. But if you don't do exploration, that means you do lose the bigger rewards, or you don't really get like good score, or you don't really do really well in the job. So you need to balance these two things. So here we follow a technique called epsilon greedy policy. I'll come back to this one a little later. So just want to read it out too. Exploration is about finding the more information about the environment. So for example, if you let's say that you are in the middle of the city, you don't know anything about the city, you are hungry, you want to go to a specific restaurant. If you have in your mind, that's called exploration. So you go to that restaurant, you eat the food that you might think is good, and that's it. But instead, what you can do is you can also explore, just looking around for other places, and just go some other place, eat something that you have never eaten before, or something like that. So that's exploration. So exploration. So if you don't exploration, you might miss eating good food, right? Like you might miss eating something you probably like. At the same time, if you do exploitation, then obviously, if you do exploration, you might miss the exploration part. If you do exploration, you might miss the exploration part. So you need to kind of maximize both of them. So just like I said, if you act greedily, so we end up choosing one action forever because that action is the best, and it's like a loop. If you can't explore, of course, you don't really find what is out there. So the way we handle this problem is following this strategy, like this algorithm you can call epsilon greedy policy. So I think I'll talk a little bit about it, but you'll understand only after you see the code. So epsilon greedy policy is a function or policy. It's like it takes best action based on some probability. So that is 1 minus epsilon probability. Let's say this epsilon we set initially 1. That means even though you know the best action, you take the 0 probability of that action, because initially you want to explore the space of the environment. You want your agent to interact with the different parts in the environment to see what happens in that state, what happens in that state. So of course, if you have epsilon is 0, that means you're pretty much sure, like the best action is the one we should do it. So initially we set the epsilon 0. Initially we set the epsilon 1, sorry, and we gradually decrease the epsilon as we iterate this process over time. So basically to handle the exploration and exploration part. Yeah, initially we set 1, then we reduce it for every iteration, and finally we choose the best action. So I think you'll understand epsilon greedy policy when you see the code only. So I think I'll just summarize the concept just one more time. These concepts are pretty much important. One is policy function. Basically it maps from state to action. You can think like a black box, or you can think as a function. You give the input, you get the output. The input is state, what state you are in. The output is what action you should take. Basically it gives the output. Of course, a deterministic policy and stochastic policy. Deterministic policy is like it gives the exact action to take without a question, and stochastic policy gives based on the probability scores, like 80%, 30%, 20%, sorry. And another important is value function. Of course, it's like a score. Basically you estimate the score, you estimate future total reward by just at a given step. So you can do either state value function or action value function. If you know what state you are in, you can pretty much expect in the future that I get this by following state value function. If you already know action, then you can take action value function in order to expect the future reward. And these are just like normal, and this is for optimal policy, like the best policy at the end of the training. And this is both for both state value and action value. And two types of task: prediction task and control task. The prediction task, we just give the policy is given. That means you don't really improve the policy. You don't really improve the function of we don't improve the policy function. You only focus on calculate the value function from that policy. In control, policy is given, but of course you improve the policy to get the bigger rewards in the future. So majority of the tasks are control tasks, but you can combine both of them in a way that you can solve the problem that you are actually on. So on policy and off policy. So on policy is like you only have one policy function, and it tries to learn on the job. Off policy, you can have two different policy functions. You can improve one policy by using the other policy, basically. So you will see off policy learning. Off policy learning is what we use for QLearning. So you will see while we talk about while I show you some code. And exploitation. So we don't want to explore too much, and we don't want to exploit too much. We need to have some balance set. We need to make sure that we explore enough in the environment while performing better. So this is where the trick of any reinforcement learning problem is. And that's where I stop a bit. If you have some questions, I'll probably take. Let me know if you have any questions. I'll try to answer the questions based on what I said so far. Let me know if you have any questions. All right, I don't see any questions, so I'm just gonna move on further. All right, so QLearning is, so I think we, as I told in the beginning, I really didn't cover a lot of concepts in reinforcement learning. So there are like two different concepts. One is like, I think we already seen like off policy learning and off policy learning. So QLearning is an off policy learning method. Basically, it uses two functions to improve the entire program. So this is probably one of the most important breakthroughs in RL. So I'll try to summarize like what QLearning does is. So you can see the figure. It's like you can think this is a state 1, state 2, state 3, 4, 5. Let's say. Okay. So this is a state, and this is an action. The dotted one is full action, and this is a state, and here you get the reward. Basically, when you have an action, you perform the action, you go to another state, you get a reward in center. So QLearning, the name QLearning, Q already we know that is like value function we use. So it estimates the state value function for a target policy. So target policy, okay, you may be confused in the beginning what's the target policy. You can think like this is one policy and two policies. So it uses one policy to basically choose what action to take, while it uses the other policy to improve the program. So here I said like this, it estimates the state value, action value. That means it tries to find a total expected reward by following the target policy that deterministically selects the action of highest value. So deterministically means it gives 100%, like it says that you have to take this action without a question. So I'll try to explain the diagram, because if you understand this diagram, I think you can pretty much understand most of them. So imagine you are at some state, let's say a year, and you want to take some action. So let's say you have a policy in the beginning, you have random policy, it gives a random action, of course. So you get an action, and you take that, you have the state, you take that action, and based on that action you get either reward either positive reward or negative reward, and you go to the next state, which is s dash year. And again here you also have like multiple options, like multiple actions, and here also you ask the same thing, hey, I'm in this state, what action to take. So you call this target policy, and it gives an action, and you choose that action. So this target policy gives the best action basically. So it analyzes all three actions, it tries to check, it tries to see which one has the highest value basically. So here if this is the highest value, it gives the highest value. So it maybe this equation might be intimidating a bit. I think I'll show you, I'll talk about this entire thing while I show you the code. So as I said, it uses one policy, which is like target policy or greedy policy call, to choose the best next action here, while following the behavior policy, which is explore greedy policy. So greedy policy takes action deterministically, behavior policy takes action using the epsilon greedy problem. So this is one. So for example, agent starts in S1 state 1 and performs action, which is action 1, and gets a reward 1 would be negative or positive, and goes to the next state, which is state 2. Now the agent looks at the maximum possible reward for action in state 2, sorry. Same thing what I said in the beginning. Here when you have a state, when you have an action, you perform it, you get the reward, you go to the next state, and again you ask what action to take. The policy function gives the best action. The policy function here is the target policy function. We'll see about that a little later, I guess. So just these are notations. As current state, a action state, or current reward, as that would be next state, and of course a dash would be next best action. So this is the next best action, this is the current action basically. And when you are here, this is the current action, and down would be the next best action. So okay, these two things probably I think you'll only understand after you see the code. I'll quickly try to show you the code. So basically what it does is, oh my god, I'm using, seems like Windows here. Alright, so I'm just going to create a system here just to give you, so which is like, this is state 1, state 2, I'm sorry, state 3, and this is action 1, action 2, action 3, action 4, let's say. So this is the table I'm giving. This is like state value function table. Oh god, I think I can't write here. Value function table. So this is the value function table for every state and for every action. For example, action 1 at this, if you're at the state 1, and it takes the it gives the score for all the actions. Let's say action 1, it takes only one. Oh, sorry. For action, if you're at the state 1, it gives all values for these actions. Let's say action 1 would be 2 points. I'm just making this up. Would be 3 points, maybe 4 points, maybe 5 points. Let's say you are at the state 1. So which action to take based on the score. So obviously you take the highest value, which is the 5, then you take the action 4. So if you're at this S1, based on this table, you take the action 4 because that seems like a best value. So maybe then if you take this this value, it goes to the state 2 or state 3, depends. Let's say it goes to the state 2. Again, it tries to figure out what value, or like what action to take, and it tries to predict these values. Again, it predicts it maybe 10, maybe 0, maybe -1. I'm just making this up just to give you some high level. So again, so the best action to take here is action 1 because 10 points. Then it goes to the S3, let's say. Then again it tries to predict the what values will be, maybe 1, maybe. So here the best action to take is action 1 because that's the highest value. So the reason why I draw this table is, this table is basically what Q function, what this basic traditional QLearning algorithm does. Programmatically we can create a table where we have the table as states and action pairs, and these are the values, what is future expected rewards. So these rewards are predicted by the algorithm. Of course initially they predict really wrong, but based on the environment you interact, you change this table. So based on this table, these values get updated over time. Initially they might be like this, the next time at the next iteration those values get updated here, and the final, let's say training is done, let's say this table gets updated, then you know what action to take. If you're at the state 1, you take the highest value, which here is state 4. If it's state 2, the best action is action 1. If you're at the state 3, the best action is again action 1. So this is at least for the vanilla QLearning algorithm, this is how it works. So now I'll try to okay, so Q value function, action value function, we know that it takes 2 parameters, one is state, another is action. So you give the input, you give these 2 inputs to this function, like let's say you give state, you're at the state, let's say here, assume there is a like this, there is a state here, and you give the state, you give some action. That action is randomly, let's say initially you take random action, and it tries to calculate this entire thing to give you some score, like what action, what's the score like this by following this one. So I'll try to I explain here only. So let's this is state, this okay, let's say you are at the state, this is state and this is action, A1, A2, A3, just assume that state here A1, A2, A3. Initially the Q table would be, everything would be, you can initialize the Q table like however you want, mostly zeros. Let's say you initialize everything like 0, 0, 0, like, because those values are initially, you just start with nothing, everything is 0. So now of course you take the initial state, which would be S1. Now here you look at the table, what action to take, and of course everything is 0, then of course you can take randomly. So you take this action, let's say action 1. So you go to the next state. Here when you have the state and action, you get a reward. So that reward basically is this, yeah, here. So ignore just focus on this one first. When you have a state, when you have action, you perform into the environment, and that gives the reward, which is the R. That reward is absolutely fine because you define the rewards. Remember that for any RL problem we define the reward system right in the beginning only. So when you have state, when you have action, you perform into the environment, then you get the reward, which is absolutely right, because you define the reward system. Plus here you had like what is the next, you predict what's the next best action. So this is what it does. The next best action would be, so again you give the next state instead of the current state, you give the next action. So here, 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 and you take the best value out of it and you combine both of them. So that's what this entire function, this is one. So if this is done, then this is the same as this, like previous one, and this this alpha is just, you know, wait it, you can ignore alpha for a while. If you're a beginner, you can ignore alpha for a while. So what it does is, to calculate the current state, I take the first, I had the what are the current value I have in this state, plus what is the reward I get, plus what is the expected reward I get next state by taking the next best action. Here I subtract the what's the previous value before, because you need to verify it, like, you know, so this is the prediction, this is the real one. So this is the actual prediction, because the next best action is the prediction one, and this is the current value of it. So you subtract that in a way that you get some score and you add that to the current one. So again you do it like, you know, multiple times, you update it again and again, and final. So I think I'm going to show you some code to understand. I have these codes, TD, you can, I have the links. Yeah, we have, okay. Yes, here is the code for just vanilla QLearning. It's not deep QLearning, it's just vanilla QLearning. So here I take environment, this is a cliff walking environment. So if you don't know, if you're not familiar with this environment, it's just very basic, like four you can visualize like a matrix with 4 by 4, like just 4 or 5 states and 4 or 5 actions basically. So epsilon initially I said like 0.1, and gamma would be 1, and alpha would be 0.1. So basically, so this is epsilon greedy policy algorithm. So basically, so it takes that Q is a, wait a second, I think we'll come back here first. Okay, so if you recall it, epsilon greedy policy takes best action based on the probabilities, based on the probability, which is 1 minus epsilon. I think you can, basically what it does is at any point it predicts the what action to take with some scores, like 90% of action 1, 10% of action 2. So you take the either 90% or 1% based on the probabilities. So this is the actual main algorithm. So let me try to understand this one. So first Q, we initialize the Q is just same as this entire table, states and action. It's like, you can imagine this table is Q, and we initialize that Q with I think all zeros. So action, so environment, okay, I use this environment, it gives some already values, predefined values, which is action space would be, let's say 5 action space, 5 by 5, you know, something like that. So I'm not sure, like, because it's been a while actually, so I'm not sure how many states or how many actions are this, but you can imagine a 4 by 4 grid or 5 by 5 grid, this one, you can imagine. So so here we train it for certain number of episodes. So you can think episodes are kind of like epochs in deep learning. So in deep learning we run for, like, you know, certain number of epochs, right? The same way here episode. So an episode we call when the game ends. For example, if you try to apply the try to solve a problem where at a certain point the game or the entire thing will end, then we call that episode. If it doesn't end, then it's a continuous space. So we assume that most of the time, like we create environments which are like at which will end at certain point. So we you can take as many episodes as possible. Of course, the more episodes it would be better, but also it would be worse. It depends how the agent performs it. So I take the current state. So this gives the current state. So randomly, let's say, now I do this entire loop. This is like true means like at every time you try to interact with the environment might say either this is the end of the game or not. So if this is not the end of the game, then you do this action. If this is the end of the game, then you take the next episode. That's it. So of course initially it's not the end of the game, so you go here. So here first you follow the epsilon greedy policy. So now you have the current state. So you call this policy. This is the policy function at this time. This is the policy function. So you have the current state, you give to the policy function, it gives you what action to take, and basically it gives you the score, and you take the scores based on the actions. So if you give the current state to this function, it gives the probability scores. Let's say 80% of the state action 1, 20% of the action 2, and based on the score you choose randomly. So of course if even though it's 90% of action 1, based on this random nature, you may get action 2 also. So now you have the current action and the current state. So you step into the environment, so you perform step, so you get like a couple of points here. You enter into the next state, which is pretty clear. You get the reward, and you can this done means whether the game is over or not. So that's here. At this time you got the next reward, you got current reward, next state, current state, queue, everything you have. Now you just look for the next best state, which is same as this. This is the next best state. So next best state would be in the queue table. You take the next state and you try to predict what is the best value in this, which is same as here. Here we choose the best value of this. Here this is same as this function. So argmax, of course you want to take the index of the max value of next state table, which is same as, let's say this. If you are at state 1, state 1 is the next state, and you try to look all the states, what is the best value here, and you choose that action. Which gives the index value, and that's the best action. And of course now you have the next state, the next best action, and you get the score from the table, and you apply gamma here. As I told, gamma is just discount factor, mostly 1. Then you have the current reward, you do the target. Okay, just these two equations same as these two. And you just update the Q value here. If it's done, break. If it's not done, you just repeat again one more time. So of course the current state would be the next state, because you want to iterate this loop. So based on this loop, this runs many times. Once the environment is once the environment says that okay, it's the end of the game, then it gets cancelled, then this is cancelled, then it goes to the next episode. So after running like many epochs or many episodes, many iterations, you will update this Q table here. At the final you get the Q table like here, like this. Here we have I think 47 states basically. Actions are 1, 2, 3, 4. So it's like 47 by 4 matrix. It's not like few states. 47 states we have, and we have like these values. And of course in some states have 0, 0 values, while the other states are pretty good. Negative, positive depends on the reward system. We can't say at this time. because we're not seeing the reward system, how the reward system works in this environment, because this is not, we don't control this. This comes from the environment, and we don't control the next state, we don't control anything. So obviously we assume that this environment is pretty good, so that gives the reward system. Based on the reward system we get some scores, and based on the scores it takes the best actions. So I think that's pretty much it for the QLearning. Basically you can, I'll try to summarize it a bit. First, main important thing would be this: you follow some epsilon greedy policy. Based on the score you take the action. This is epsilon greedy policy, and this is deterministic policy, because in this policy you take the next best action without any probability. Here you take the next action based on some probabilities theorem. So you have two functions here, policy functions. Just like I said in the beginning, you have behavioral policy and target policy. So this is like one policy which gives the probability scores. Even the probability is higher for one action, you don't necessarily take that action because of this randomness, because we want to explore the space. Even though we know that 90% this is the best action, you still can take the wrong action because you want to explore the space. But here, if it's the best action, you take it. You don't really stop here like to see whether it works or not. You just take it whatever action. So here like two policy functions here. If you see, this is one policy function basically, and this is one policy function. So I mean to say function, which means which gives like which action to take. This is absolutely greedy, and this is based on some probabilities here. If you understand these two, I think you can understand deep QLearning, because deep QLearning same as QLearning, except instead of this we use, instead of this Q table we use a neural network basically. That's the only difference. I'll try to show you the code for this. So anyway, if you want to head over to this one, I'll add this to link, I guess. Yes, so this is the deep QLearning, the deep Q network for Atari games. So the environment here is, I take Atari games. So so this is the same code that I showed there. So this is where the deep QLearning works. So just like I said in the beginning, you can have if you have some task where the state space is limited or action space is limited, we can use QLearning. But if the task has like infinite state space or infinite action space, then of course taking the million or 1,000 by 1,000 or million by million grids don't work in programming. So obviously we need to find a different way to solve that problem. So which is why we use neural network. So here we see in Q, this is completely like 47 by 4 grid. But if you have states like 1,000 or million states, then you can't really have the this one, which is why we use a function approximator like a neural network or even simple machine learning classifier. Doesn't matter actually. So here is the one. So you have a state. Let's talk about this one. You have a state. You create a network, which is of course a neural network, which is black box at this time. So you give a state or a couple of states to that network. It tries to give the action value scores. It predicts these action value scores basically. So this is a regression problem, you can think. So not classification problem. So it just, you give a state, it kind of calculates the Q value for every state, for every action. So Q value 1, let's say 10, 20, 30, and it takes the best one basically. So this is one architecture, and the other one would be this. You can give state and you can give action also, the current action. It goes to network and it predicts the Q value of a particular action. So that's it. This is the only difference. Other than this, everything would be same. So instead of this grid, instead of that the matrix, we use the neural network. That's the only difference between normal QLearning and deep QLearning. Of course, the neural network job is to learn the parameters inside, like what kind of states go in there, what kind of outputs I need to get. So once we train this entire neural network, at the time of prediction, we use this trained neural network to predict the next best actions. This is the one. So after training is done, let's say you give a state, it gives the next best action. So based on the next best action, we make the decisions. So I think I'm just gonna speed reading a bit. So supervised learning plus QLearning would be deep QLearning, because here you use a neural network. So neural network means you need to have labels also. So this is how the loss function works basically. We use L2 loss since it's a regression problem. So you have predicted, you have actual value, actual total reward, you have predicted value, and you subtract it, and just to avoid the negativity, you just do this one. The training and everything would be same only. I think I'm going to show you the code directly instead of talking here, because the code makes more sense, I guess. So this is just an algorithm. You fill with okay, I'm just going to show you the code, then I'll come back here. Oh sorry. Yeah, so here I took there's a paper in 2013 by DeepMind. They actually discovered this algorithm. They use Atari games as environments. So they take like a bunch of Atari games, they created this DQN, and surprisingly the DQN actually surpasses the human performance of some of the games, some of the these arcade games, I guess. So they, of course, this entire algorithm was developed by them, and they fine-tuned a bit, so this is the big paper. Basically this is the big news. If you try to see what DQN, basically you will end up seeing the paper and the first results of the search. So just want to explain, GYM is the environment. GYM is a tool for the reinforcement learning environments. So this is the environment we use. Break deterministic version 4. I assume you already know a bit. If you're into, if you're not into, just think like this is the game basically, where you have a ball, you have a pad, you try to hit the bricks over the ball. So, and this algorithm, what it does in this particular problem is it takes the pixel values of the video game, and it tries to predict what action to take based on the pixel values, based on the image. And the image has 84 by 84 by 4, so 84 fixed window, and 4 channels RGB. I think these 4 channels, you don't have to worry about the 4 channels. Why? But you can think it's just a picture. It could be black and white picture also, it doesn't matter. 4 channels would be 4 frames together, they stack it. So this entire code is to just pre-process the frame. It's a computer vision thing, I think. So this is the main one. Okay, I think this is okay. So this is the epsilon greedy policy function. Same thing as we seen before. You have the current state. You try to take the random action based on the probability theories. So the algorithm is same, but I write in a different way here and there, so you can probably understand by taking a look later, I guess. So I think I'm going to skip all of these things which you can understand like by yourself. The main thing is the actual algorithm here. So this is the main function for this one. So in this particular program, what we take the images as observations. We store all of these images somewhere, like in the memory, like yes, here, no, wait a second, yes, here. So this is where we start. Like, let's start this one. So we just define number of episodes, how many times we want to run, and these are some extra variables. Of course, we first take the current state randomly, and you can ignore this for a while, and this is the pre-process steps for these frames, and here it is from now. The first, when you have the current state, you follow the epsilon greedy policy to get the action. You can ignore this. This is entire thing based on the environment. You can ignore this. This is based again environment. Basically, you just decrease the epsilon value. Initially, you set it high. You reduce it over time. So you perform the action, real action, whatever action you get it, you perform here, and you get the next state reward. Based on the game, you get the lives. Again, you get the next state. You process this. This is again image pre-processing. This is based on the game. So basically here what I'm storing is I'm trying to store all of these images into one particular memory, like replay memory, a buffer. Later I just take these images from the buffer. So again this is the memory buffer. I just appended all of them, current state, action, reward, and here. So I do this for like certain number of steps. Basically I do this for certain number of steps. Once I get the heavy memory, then from that point onwards I'll start to implement the deep QLearning algorithm here. So let's say the episodes, we have 10, 20, 30, whatever number, all the images, all the states, everything will be stored in this buffer here. Then I apply the deep QLearning here. So let's go back here, deep QLearn. So here now you pull the data from this buffer. So data is the current state, action, rewards, next state, there. So I'll try to summarize it a bit. So we have the current, so first we have two models here. One is the target model. The target model predicts what's the next best action, which is going to give you the next Q values, and based on the next Q values, I think this is like kind of like a difficult thing to explain, I guess, because there are so many things which involve based on the game. You need to, I think it's better like if I explain this over here, because so many in that particular example, I think so many things are based on the environment and processing only. I think you don't really much understand. You might be confused. Even I'm getting confused just referring which one is this. So I'll try to explain this only. As I said, like we store all of these states, current actions in the memory, like a replay buffer, and we pick from that buffer. So we have here two neural networks we have. One is we initialize the network with random parameters we call theta, and the other one is theta dash. You see it, training network and target network. So just like we said in the beginning, like two policies, right? Two different policies. One policy is going to try to learn the environment, while the other policy is going to make the decisions. So just like that, here we have two different networks, training network and target network. We'll see what network does what. For every episode, just like for every epoch, we take the of course we initialize the environment, we pre-process it, it's extra step. And for every time step, so for every particular, like episode wise, for every time step, first we take the we follow the epsilon greedy policy, which by taking the training network. Here you see theta, this is the training network. Here we take the just a second, yeah, okay, sorry, so here yeah, I think it's same, or like I got confused a bit because theta and theta dash, which one is theta dash? Okay, so yeah, first we take the current state and current action, and we follow this training network. Based on the training network, we take value, either random action. This is epsilon greedy policy, which are in probability, and we get the action, we perform the action, we have the current state, we have the action, we observe the reward, we go to the next state. Of course, we process the next state here, and we store experience, all the experiences in a buffer here, but you can ignore this step. So now the first time step, we take the random action based on epsilon greedy policy. Oh, sorry. This is done, and the next here we follow these. We calculate the targets, actual and target y values, and this is how it works. Now here it predicts the next best action by just following the other target network here, which is not getting trained at this time, but it's still in the memory. So we have the reward, we have the next best action, and if it's a dead or something happened, then it's -1, or otherwise it's a positive reward, and we have a 2, and we calculate these loss, predicted loss versus actual loss. So actual loss we take from these the training network, and the predicted y would be based on the target network, because this y is getting calculated based on the target network, and this is training network. That's it. We calculate this label, we calculate these values, we have the label, we have the predicted output, and we just calculate the loss, and we rate it with respect to theta, which means training network. So we improve the training network first, and after certain steps we change the training network weights to target network weights here. So this after certain steps, like after let's say 1000 steps or 2000 steps, or we change the weights. Both at this point, both of the networks are same. At this time, this network is getting trained, but this network is not getting trained. After certain steps, they're both same, and you move on, like you train. So we do this for certain number of episodes. However, like it depends on the environment. For certain environments, it takes forever. For certain environments, you have to observe that, like how it's working, and this loop continues, and that's pretty much it. Yeah, I think I showed here. Basically, this is the same code as what I've shown before. Only I think you can get a better view over there only than this one, but with the same algorithm, the epsilon greedy policy same, and mostly same only from this only. You can get a better view there only than here. Take a look at this one. This code is written in Keras. The main neural network is written in Keras, with some convolution layers, and I think this was written way long ago. Probably there are many versions out there, I guess, but this works. If you try this on a particular environment, I think this code pretty much works, but I think you can reduce the code by just writing in a different framework. I think if you use PyTorch, I think it's pretty much, I think I've written for Python, but I don't think I have on my GitHub, but I'll try to share it with the community if I have something. So I think in PyTorch you can write this entire code in just like, I think maybe less than 100 lines, I guess. Or I think here it's more too much complicated. And that's pretty much it, I guess. So I just gave only the eye-level idea to get you started. As I said in the beginning, it's kind of really complicated to explain each and every single aspect of particular algorithm, particular program, particular just concept. So if you have any questions at this time, I'll try to take this before I wrap it up. I'll try to see if I have any questions. How do you define invalid actions for specific states? I didn't fully understand what you mean invalid action states. So I have to assume something here. So I don't really clearly understand what you mean by invalid, basically. So I'll try to assume something. Environments, maybe wrong actions, like, is that what you mean? I'm not fully understand your question, so I don't think I can answer that at this time. So I think that's pretty much it. If you have any questions, let me know. Okay, this is one slide probably. So this entire slide gives the high level idea of what deep QLearning is. Just take a look at it. This is whatever we said so far, everything is over there. And so these are the guides, and I've written a couple of articles, so you can pretty much go through these two. And the code, everything code would be on GitHub, so you can follow these links. I put these links in the slides, so I'll let you know. So in deep learning, I have like entire set, some model-free reinforcement learning algorithms and model-based algorithms and deep. So you may have to check some Monte Carlo, TD. So we discussed TD only, temporal difference, but I did not mention temporal difference at all. So I just directly jumped to QLearning. Yeah, just take a look at these things. Maybe you may find it interesting, even though they are like outdated a bit, but still to understand the concept, I think they are pretty good. But you can even reduce the code by just putting in a different language, I guess, a different framework. With that, I think I'm pretty much done. Like, if you have any questions, of course, I understand that, like, combining everything in just one particular session is kind of difficult to explain. But if you have any questions, feel free to write to me, and I'll try to answer them. I'll try to give you a good view of them if you